Okay, let's do an example problem for electric potential or voltage of point charges. All right, so this is a problem that I assigned in homework. It says a 1.92, of course my numbers will be different than yours, a 1.92 microcoulomb charge, Q1, is 1.33 meters from a second charge, Q2, which is negative 5.77 microcoulombs. Find the electric potential at the point A right here, which is 3/4 of the way from Q1. So obviously this picture is not the scale, because it's saying that that distance right there is 3/4 D. So it's obviously not the scale. All right, so we want to find the voltage, the total voltage. This isn't that bad because voltage is a scalar. All right, so we start with the equation V equals K times Q over R. This gives us the voltage at a point in space at distance R from a charge Q. And so here what we would have is we would have the total voltage at point A equals the voltage at that point due to Q1 plus the voltage at that point due to Q2. So that will equal K Q1 over the distance from charge 1 to A, which is 3/4 D, plus K Q2 over the distance from Q2 to A. Well, this is, again, the picture is not the scale, but if the total distance is D and the distance from Q1 to A is 3/4 D, then the distance from Q2 to A is 1/4 D. Okay, so there's our setup. Now we just plug in the values that are given to us in the problem and solve for the total voltage at point A, VA. So one thing we can do algebraically before we solve is you notice that both terms have a K in the numerator and a D in the denominator, so I can factor that out, and I'm left with an expression that looks like this. And then plug in K is the electric constant. It is, forgot the power there, 8.99 e to the 9th newtons meter squared per coulomb squared. D is 1.33 meters. Plug in Q1 and Q2, and then solve. So we get an answer of negative 138,700 volts. Okay, so that completes part A. Part B says, find the point between the two charges on the horizontal line where the electric potential is 0. This requires a completely different setup. So let's start fresh. Okay, so now we're looking for the location of a point. We can call it A again, and it's some distance. Let's say X to the right of Q1, and if the total distance between Q1 and Q2 is D, then the distance from Q2 to A must be D minus X, like this. Okay, so we're looking for a scenario where the total voltage at A is 0, and the total voltage is the voltage due to Q1 plus the voltage due to Q2, which is equal to K Q1 over X now plus K Q2 over D minus X, and that equals 0. Okay, so now we need to do some algebra and solve for X. X is the unknown distance to the right of Q1 where this total voltage is equal to 0. All right. So the first thing I did here was I added, or actually subtracted, the K Q1 over X from both sides. So I get minus K Q1 over X equals K Q2 over D minus X. Now what you notice is there's a K on both sides, so that will cancel, and now I can cross multiply numerator by denominator. That would give me minus Q1 D minus X equals Q2 times X. And now the next step is to distribute out on the left-hand side. So minus Q1 D plus Q1 X equals Q2 X. Okay, now I'll subtract the Q1 X from both sides. giving me minus Q1D equals Q2X minus Q1X. Now I'll factor out the X on the right-hand side. That gives me minus Q1D equals X Q2 minus Q1. Now divide both sides by the quantity Q2 minus Q1, and I've solved for X. So I get X equals minus Q1D divided by the quantity Q2 minus Q1. Now plug in my values for Q1 and Q2 and D, and I solve for X. And what I get is X equals 0.33 meters. So the point along the horizontal axis up here, where the voltage is equal to 0, will be somewhere about 0.33 meters to the right of Q1. All right, let's move on. Okay, so here's a problem where you have a circuit where there's 3 capacitors. 2 of the capacitors are hooked up in parallel, are wired up in parallel. Let's call that C1 and C2. And then the other capacitor, we'll call that C3, is wired up in parallel, or sorry, in series with the other 2. So C1 and C2 are hooked up in parallel, and the rule for combining capacitors is that if the capacitors are hooked up in parallel, then their capacitances add. So the total capacitance of capacitor 1 and 2 would equal the capacitance of capacitor 1 plus the capacitance of capacitor 2. 10 microfarads plus 2.5 microfarads is 12.5 microfarads. All right. So now we can think of this circuit as an equivalent circuit where you have one capacitor that's equivalent to 1 and 2 together, call that C12, in series with C3, like so. So now this new combined equivalent capacitor, C12, which is equivalent to those 2 capacitors in parallel, is in series with C3, and the rule for combining capacitors in series is that 1 over the total capacitance, call it C123, of those capacitors in series, is equal to 1 over the first capacitance plus 1 over the second capacitance. So now you got to do a bit of algebra. If what we have here is 1 over the total capacitance, then the total capacitance, C123, of the entire circuit is 1 over C2, 2 plus 1 over C3. And that's equal to 0.293 microfarads. So one thing to note is that when capacitors are in parallel, the combined capacitance is greater than either of the individual capacitors. But when capacitors are in series, then the combined capacitance is less than either of the individual capacitors. And so you can see the total capacitance is less than the 0.3 microfarads of capacitor 3. All right. Okay, let's move on. So here's a question dealing with the connection between voltage or electric potential and electric field strength. So here it's talking about, well, it looks like a physicist wrote this and not a biologist, because they're saying the voltage across a membrane forming a cell wall. Well, a cell wall and a cell membrane are completely separate things, but let's roll with it. Is 84.7 millivolts, and the membrane is 8.72 nanometers thick. What is the electric field strength across the membrane? And it says it's surprisingly large, but it's correct. And it says, importantly, assume it's a uniform electric field. So what you're supposed to assume is that this plasma membrane of this cell is effectively a parallel plate capacitor. And let me draw a picture. Okay, so here it is. You have a cell membrane that has some thickness, and the thickness is, in this case, D is 8.72 nanometers. And there's a voltage difference across the cell membrane. And that's because the outside of the cell is more positive than the inside of the cell. And there, outside. Okay, so you can think of the 2 sides of the cell membrane as the 2 plates of a parallel plate capacitor, and there's an electric field pointing from positive to negative between these two plates. And that electric field, we're assuming that it's uniform. All right, so when we think back to what we talked about in class and the last video, the connection between voltage and electric field is, at least in terms of magnitude, the change in voltage, the difference in voltage between the two plates is equal to the magnitude of the electric field times the distance between the two plates of the parallel plate capacitor, okay? So in this case, it's not plates, it's the sides of the plasma membrane of a cell, okay? So now we solve for E. E is going to equal the voltage difference across the membrane of the cell divided by the thickness of the cell. And that's equal to 9.71 times 10 to the 6 volts per meter. And I had to be careful there because I had to be careful of units. 84.7 millivolts is 84.7 e to the minus third volts. And 8.72 nanometers is 8.72 e to the minus ninth meters. Okay, so I had to be careful of units. Now, you know, so the units here are volts per meter. Remember that another unit for electric field is newtons per coulomb, and they're equivalent. You can convert newtons to base units and volts to base units, and you can reorganize, and you can see that volts per meter and newtons per coulomb are exactly the same units, just in different combinations. Okay. And it is, in fact, surprisingly large, but it is correct. That's the strength of the electric field across the plasma membrane of your cells, because the numbers in these in this example are fairly realistic for actual cells. All right, last problem here. What voltage in kilovolts must be applied to a 10 microfarad capacitor of a heart defibrillator to store 500 joules of energy in it? Okay, so to answer this question, we need to know the connection between the energy stored on the capacitor, how much charge is stored on the capacitor, and capacitance. So one way to write the amount of energy or potential energy that's stored on the capacitor is that energy is equal to 1/2 Q, the charge on the capacitor, times V, the voltage at which that charge is stored. But this formulation isn't going to be too helpful for us right now, because if you look at the information given to us in the problem, what we have is we're looking for a V. We're given the capacitance of the capacitor, that's C, and we're actually given the energy that's stored on the capacitor, 500 joules, okay? So we don't know Q. In fact, later we're asked to find what Q is. All right, so this equation isn't going to help us by itself. We need a different tool. And that tool is the definition of capacitance. Capacitance, C, is equal to the ratio of charge, Q, divided by voltage, V. Or in other words, capacitance is charge per unit voltage. All right, so we actually use this equation and combine things to solve for the things that we don't know. So we can write that Q equals C times V. Therefore, the energy, potential energy, is equal to 1/2 times C times V, or 1/2 CV squared. In other words, substitute C times V in for Q in the potential energy equation. Now we can solve for V. And so what we get is V equals the square root of 2 times the energy, PE, divided by C. And that gives us 10,000 volts, which is also 10 kilovolts. So the typical voltage applied to this heart defibrillator to store 500 joules of energy is 10,000 volts. So how much charge is that? Well, now we can use this equation. Q equals C times V, and just solve for Q. And that gives us 0.1 coulombs of charge. Okay, so that concludes this problem set, at least the work that I'm going to do for help you guys out in this problem set. Stay tuned for your next lesson, which will be